Hello, it's Terry Dennery of the MathWorks. So this will be our third video in this series on refrigeration. And in this one, I'm going to try to give it kind of the out-of-the-box experience. And so we're going to, from scratch, let's build a model. So let's go to our Simulink browser and let's open up a new file. Let's bring that file over here, that model. All right, let's get started. So from the Simulink browser, I come down to Simscape, and you will see in the foundation library, there are two-phase fluid blocks, and we'll be using this foundation library quite a bit. But we will also use the tool Simscape Fluids, which has, I'd say more complete, maybe a little more complex component models that will be very useful as well. All right, but let's just get started in the foundation library, and we're going to go to Elements, and we get a reservoir. Right, and we go to the Simscape utilities, and I will get what I call the f of x equals 0 block, right? But basically it's a Simscape solver block, and through that you can set various very important parameters that kind of guide the calculation. Anyways, those are two things in there. I hit run. I'm just going to kind of keep on hitting run, make sure things work. Seems to work. We calculate something, but we're really not seeing too much yet. All right, so as I've kind of figured out what I wanted to show in this presentation, I thought, well, getting the condition of the fluid is really, really important. Okay, and so under sensors, I'm going to bring in a pressure and internal energy sensor, a thermodynamic property sensor, and then I think vapor quality is always pretty interesting to have too. All right, and for those who've used Simulink before, sometimes it takes a while getting used to kind of really get the basic ideas of Simscape, right? And so I think you'll see that as we kind of put together this general sensor for the fluid dynamic state, right? And so let's create a subsystem, right? Now, we're going to do all kinds of things to kind of correct I'll say the interfacing of this subsystem, right? And it's going to basically be a probe, and that probe connection to whatever fluid node we want to will set these calculations, all right? And so I'm going to just call it A, because A is simple, right? And none of these presumed outputs or interface setups are going to be used, or we're going to use. So let's get rid of all of them, right? But again, it's a probe that's going to measure pressure and internal energy, and so I can connect all these into A. All right, so now let's just kind of make it big enough so we can see things well. Let's move that down. Probably good enough. Okay, and we'll contend initially with the thing that everybody contends with regard to Simscape, which is why are those arrows hollow? Why do the lines look different? Why does A not have a arrow on the end of the line? And what we're really dealing with here is connectivity, but we're also dealing with I'd say a physical domain environment that lives within Simulink. Okay, and it's sort of like you define boundaries here, and certainly the idea that measurements are important is it's still there, but why with the arrows? Well, that's because we have physical signals, and that pressure can be expressed in psi, could be expressed in atmospheres, pascals, megapascals, or so forth. So that's kind of a good example of the units count. You need to be very attentive to them as you use this tool, right? And so anyways, for a variety of reasons, we have come up with this configuration for dealing with this, and it's called the PS to Simulink converter. So physical signal to Simulink, right? And so the main thing I need to do is say, well, if I'm measuring pressure, I want it to be in megapascals. That's my choice right here. Okay. Now, we got a bunch of these, and so I'm going to just kind of set up the rest of them. And so we'll do one on U, T for temperature, H for enthalpy, V for specific volume, S for specific entropy, and then X for the vapor quality. So if it's, I believe if it's a 1, it's fully vaporized, and if it's a 0, it's fully liquid. That's what two-phase flow blocks are about, right? And this block's a little bit different than these, where these are direct nodal measurements, right? This one is a reference that we measure, pressure and internal energy, relative to a standard, or at least another location, right? And so I'm going to bring in the absolute reference, which you could think of it as absolute 0, and that will give us measurements on these things. I think that it will serve our needs quite well, right? So, and we put in that absolute reference. And then, part of this seminar, and we're not going to be so super attentive to it, but it's basically this idea that why would you do this in Simulink? Well, it's because Simulink is loaded with all kinds of great stuff. That's the short answer. And we'll probably see that a number of times, but here's a specific example where I believe we're seeing that, and that's the use of these buses, right? And so let's go ahead and configure this. And so it's going to have 7 entries, right? And with that, we'll have a single output port, right? And this I'll simply call M bus, M for measurement, okay? And we'll come back up and we'll kind of see what all this looks like right now. Now, we certainly are not done yet, but we're developing a fundamental component that's going to, give us thermo state, right? And we'll probe into it like that. Okay. Anyways, let's kind of finish this up, though, right? And so I'm going to bring that in like that. This will go into the second. Let's just do all of them like this. Let's see. Might be a little bit of effort. I think I shortcutted something we need to do. Okay. All right. And, oh yeah, here it is. Now, if you inherit, especially if you like metric units, meters and Kelvin and kilograms, going with inherit usually works quite well, but I'm going to be pretty specific here. I'm going to go kilojoules per kilogram, right? So it's a specific internal energy. And then I'm going to go to this H1, which will have the same units, and so I'm just going to drag that in, right? And for temperature, I'm going to be very specific because Kelvin is my favorite, so let's put in Kelvin. Now, specific volume and entropy, I doubt we'll use in this. I'm going to just kind of leave them as they are. And then X is really unitless anyways. It's really kind of the fraction of vapor. So I think with that, we kind of have it set up pretty well. And then the last thing to do is to kind of deal with the fact that I don't want to call them signal 1, signal 2. I want them to have their true names. And that this is done by the fact that we can label these signals. And so I'll just call that one P, U, T, until P, of course, is H. I'm pretty much just going with the labels off the block, so I'm using small u, not big U, for my specific internal energy. Let's go here, entropy, and then this last one is X. Okay, and now when I double click on the bus, we'll see all those names are in there, and that's exactly what I wanted. Okay, cool. All right, so let's go back up here, and one of the things I love about buses is it gives you some options. You don't have to measure everything. All right, and so I'm going to go in here, and I will select pressure and enthalpy. And we'll get a scope, and we'll send those in. All right, and let's run it again. All right, and layout, put them in 2. And so we got pressure on top and enthalpy on the bottom. And I can rescale that, and I'll see pressure at 0.1. And if you're familiar with the units of megapascals, you'll know that 0.1 is very, very close to 1 atmosphere. right? So that's our default value on it. And the enthalpy, not sure, well, I'll just say, again, for our standard temperature that we're using, 293.15, for the fluid that we're operating with, that's what your enthalpy will be. Also, again, at atmospheric pressure. All right, and so now I want to be a little bit more specific, like, where did all that come from? Okay, and the clearly, the alcohol will have different material properties than water, and refrigerants in general, because they do boil at such low temperatures, have vastly different properties than water or air or any other fluid you might think of. All right, so of course fluid selection is real important. And here's where I like the options. I mean, I can kind of show it to you in the foundation library, but you'll see, the important properties will be things like critical pressures and essentially a range on, like, internal energy and pressure and stuff like that. Let's see, where are those things? Yeah, you'll see lots and lots of arrays, tons and tons of data, really, actually, if you truly unpack this thing. But I don't really want to do it that way. I'm not good enough to load in the proper arrays that are going to describe the variation of all these different thermodynamic properties. All right, so anyways, let's get to fluids, utilities, and let's get a fluid definition block right there. All right, and let's see. Okay, yeah, this will be one of our longer videos, is just checking the time. So we're about 11:50 right now. Okay, so anyways, let's go here. Let's actually run from the scope itself. And you'll see that, our default fluid clearly was water, because nothing changes here, and that's the default assignment right there. Not sure what R718 means, but I'm sure there's specifications and standards and stuff like that for water too. But we're going to use one that was used in our initial demo, and it's called R1234YF. And with that mere selection, we rerun this, and we'll see that at 200 and, what did I say it was, 293 degrees Kelvin, that's considerably, much larger amount of enthalpy, right? So materials do count, or the fluid properties do count. All right, and so now I want to go into what I think is one of the coolest features, and probably one of the most essential features of developing this type of thermodynamic fluid system, which is, let's see how we do on the, let's see, can I open that yet? Maybe I have to run the model. Oh, here it comes. Okay, let's run the model. And again, we're not doing much. What we're really doing is just probing into, into a fluid source. We're not even moving the fluid yet. And that we're seeing where it is defined in terms of enthalpy and pressure, right? And and this is probably one of these things that we should kind of clean up, but again, it's a new tool and we're still kind of, refining it. You have to actively choose instead of going with the defaulted water, let's get a two-phase fluid. And with that, then you'll see that measurement superimposed on the thermodynamics for R1234YF. All right, and what we see now, where if this was water, we'd be, I guess, still very, what's the word for it? I'd say subcooled. Here we're superheated. That's on the right side of the dome of this thermodynamic chart. Just to kind of refresh your memories, if it's been a while since your thermodynamics class, that on the left is liquid. Inside the dome, underneath all this is constant temperature. You see those temperatures labeled, like 245 is that temperature right there, which is really pretty cold in Kelvin. But it's really in this space that you have a combination of liquid and gas. It's a vapor-liquid equilibrium, and then to the right of it will be superheated. Okay, so hopefully that works out pretty well. All right, and so now we kind of get into strategy of how do we even do, a refrigeration system. All right, and all we're really doing is marking kind of the things that were selected here. right? And so what I'm going to do is, instead of going with atmospheric pressure, let's go with specified pressure, right? And I forget what I was using. I think I'll try like ×3, so 3 atmospheres. So maybe we won't be operating at such a cold temperature as 245. And let's go ahead and assign what I'd call the energy content, directly with what we're seeing on that chart, so the specific enthalpy, right? And so we're going to be somewhere around here on pressure. I always get kind of confused by log scales, but let's say somewhere around there. And we want the temperature to be, I'd say, slightly subcooled, right? And so I'm going to kind of eyeball it and see how I do, but I'm going to try 170 on that. And let's hit run, and let's see where it moves that dot. Okay, so I think it can be a little bit warmer even. And so I'll put in maybe 200. Might make it even a little bit warmer. There's a reason to kind of put in the middle, but I'm going to be good with that for right now. All right, and so now what I want to do is kind of sketch out kind of the cycle in which I want to operate. All right, and so I'm going to use another one of these blocks, and this time I want to be, basically I'm going to put the fluid through an evaporator. It's going to receive quite a bit of heat, so its enthalpy will go up, and I want to put it just to the right of the dome. Okay, and so let's try 400. Right, and there's a couple of tricks here, and I think the chart in general will need to be explained a little bit. And so what I'm going to do first is delete that. Let's make the chart really big. I'll kind of explain why in a second. And then let's introduce a couple of mux blocks. All right, and so put that in there and make this like this, and okay, we'll make a copy and we'll bring it down there. Okay. All right, and so this is our way of considering multiple points. And so P will go from here, and H will go right there. All right, and now I'm going to do the same thing on here. Okay, and I think I'll introduce it again. It's good to be in Simulink, a means of kind of keeping my charts a little bit cleaner to look at. And so I'm going to go to signal routing, and I'm going to grab one of these go-to blocks. Okay, and this is now going to be called P1, and this one will be called H1. Oops. Actually, I'm gonna change this right now, and I'm gonna kind of explain this in the context of the bigger project I'm working at. And so ultimately, one of my strong recommendations will be, if you like what you see in this presentation, is that you take on since we're talking about it right now, you take on the tutorial that we're working, that I learned much of this from, right? So let's go in here, and I'm going to bring up the project right now. And this project created by one of my MathWorks colleagues. His name's Aaron McGarity, and if anybody on this call has done much with fluids before, there's a good chance you've met Aaron, and Aaron is just an excellent resource on teaching all this sort of stuff. And this is a tutorial that he created, and it's about 30 pages long, and it goes through some pretty good exercises to build a very well, it's based on a real consulting job, I guess I'd call it, that he did, and therefore it reflects real equipment in very good detail, done very well. So anyways, Aaron likes kind of setting it up with H4, then H1, starting off H4, H1, H2, and then H3. Anyways, let's get back on track. Okay, all right. And these go-to blocks are kind of cool because you click on them and you drag it and you get the block that brings it to your next use of that number, right? And so we have P4 going there, and we'll do H4 going there. And now we got kind of a quick way of redoing these things. So I'm going to delete that, copy that, paste that right there. Okay, and that this will be, again, following Aaron's notation, which is a good idea. I'll put in P1 and H1. Hit the space bar. All looks pretty good. Where's my thermodynamic chart? Let's bring that up here too, and let's hit run. And I believe, ooh, of course, okay. You always got to have an f of x equals 0 connection. And this was kind of fun. Oops, I like getting from the bigger browser. Then when I first started using these blocks, there was one that I was going, I'm not sure why they have this. You know, why would I have a infinite flow resistance? And then all of a sudden I realized, oh, this is a great way to spec out your thermodynamic cycle. And so basically it establishes connection without really including flow. All right, and so with that, we get it over there on the right. And I'd say maybe a little bit hot there. And so we might come back to that, but for right now, I'm going to switch it to 370. Okay. And so let's hit run. Okay, and so that looks pretty good. All right, and so I hit spacebar now. And so now we're going to basically do the same thing 2 more times. All right, so let's Control I, oops, no, Control R. And then let's do it one more time over here. So I'm trying to kind of geometrically, I still got these measurements that are a little bit in the way. Maybe I'll do this. Let's move this over. Put that right there. Okay, and so now we just simply use this multiple times. And that block is pretty symmetric, but I think I'll try to keep the AB orientation as we continue to go around this counterclockwise, and the A will always precede B. Okay, and so we got that, and let's rotate it one more time. Go there, and we go there. All right, and so now I'm going to just kind of look at the chart as I set the thermodynamic state on the rest of this. And I think I'll have it go maybe like 10 times atmospheric pressure. I believe that here's where I found 400 was a good number to put in. Okay, and we'll need to do this one too. And here's something that I saw later in Aaron's tutorial that I really thought was kind of cool, was this choice of degree of subcooling, right? And so we're going to increment it about 5 degrees to the left of the dome, but it will also be at that same pressure of 10 atmospheres. So I'll just multiply it by 10. And I think I got it. So let's find out. So this will be 3. And this will be H3. Okay, now we'll plug these in. And about to see another one of my favorite little features of he doing? Oh, actually, I went on the underside. I screwed that up. Let's delete that. Okay, so I think I got that right, but let's just check. There you go. Okay, so that's all looking pretty good. And so now let's put our final measurement. I think I'll kind of end the video after we do this last one. And we'll just have the next video be where we really begin to kind of spec out and create the evaporators and compressors and things like that. Okay, so anyways, this one will be, oh, stupid. Okay. All right, I'm going to just go out of order. I don't want to waste too much time on this, but the previous one should have been P2, but just to keep things simple. It's probably a quick way to do it, but let's try this. Okay, actually, here's a quick way to do it. Delete that, bring that here, and delete this, and bring that here. All right, and we'll move this over. Sorry about that error. And so now, let's bring P2 in here. I'll go between P1 and P3. And let's bring H2 in. I'll go in right there. I think I got it. So let's, yeah, that looks pretty good. All right, and so here, just to kind of summarize and maybe give a little bit of indication what the next video will be. This is a placeholder, ultimately, and that this device that takes us from state 4 to state 1 ultimately is called an evaporator, right? Now this is a placeholder for our next device, and it takes us from that low pressure of state 1 and brings us to the much higher pressure of state 2. So that'll be called the compressor, okay? And then finally, this device that essentially takes us not only to a lower temperature, takes us from a vaporization of this fluid to a liquid version of it. Okay, so this obviously, we love the word condenser. All right, and I'd say with those, I don't think we changed anything. Let's hit run. But with those changes made and those kind of labels, I think I'm kind of giving you what the next video will be, which is let's start thinking about the devices that actually, transport the fluid to these different states. So anyways, thank you.